thank you for joining our this Friday's Lockheed Martin Maryland Robotics Center seminar. Thank you again to Lockheed Martin for their continued support of this seminar series. I'm especially delighted to introduce our seminar speaker today, Professor Katia Sycara. She's the Edward Fredkin Research Professor of Robotics at the School of Computer Science at CMU and the Director of the Laboratory for Advanced Robotics Technology. She held the 6th Century Chair in Computing at University of Aberdeen in UK up until 2015. She did her PhD in computer science from Georgia Tech and holds an honorary doctorate from University of Agen. She's a fellow of IEEE, of AAAI, and the recipient of the ACM SIGART Agents Research Award, as well as the Research Award from Informs. There's a few other awards. I'm not going to read all of them out, but her research is in the area of swarm robotics. She's done pioneering work in the area of swarm robotics and human-swarm interaction. She served on various industry scientific advisory boards, including France Telecom and Siemens, and has participated in numerous National Academy studies, DARPA, ISATs, and research review boards. On a personal note, ever since I was a PhD student, I followed research coming out of Professor Sikara's group. I know some of her students very well. In fact, even now, my students read papers that come out of their group, including some very recent work that we just had published at ICRA, which builds on top of work coming from Professor Sikara's group. So I'm excited to introduce Professor Sikara and happy to and excited to see what she has to say. So please take it away.
Thank you for the great introduction, and I'm very happy to be in this giving this seminar today. And so today I thought I would give a different seminar rather than swarms and resilience in networked systems and networked adaptive systems, which I've done in the past, and still we're continuing work in those areas. Today I just want to talk about a relatively new work that we have been doing for the past year in human and agent teams, and in particular studying adaptation in human agent teams. And so, as we know, teamwork is essential to many human tasks, from healthcare to firefighting and helping people, and either remote, or we can have remote or face-to-face teams. Now, what are some of the characteristics of good teamwork? It has been shown for many years. Here I show one of the earlier papers in current directions of psychology, where they identify particular characteristics of high-performance human teams. And so teamwork basically is characterized by interdependence of the team members towards a common goal. And so the characteristics of teams, good teams, are the teammates adapt to one another, they share situation awareness, they tell each other if something changes, and so they all have mental models that are aligned with one another, they coordinate closely, monitor one another, provide feedback and provide help, and they trust each other in the face of risk. So this is what has been found by psychologists in high-performance human teams. So now what we would like to do is to have agents or robots as teammates and not just tools. We all remember the infamous Clippy, and so we don't want to repeat this not great experience. And so what we are interested in this particular study, in this particular general research that we are doing, that this talk is about, we are interested in human agent teaming, in particular in high-paced tasks where there is no communication, no explicit communication between the team members, and they can have different attributes, styles, etc. And the team performance is depends on team composition. So agents, we have humans and we have agents, and the agents could learn different policies and adapt, hopefully, to player types, to human player types. So basically what we want to have human and agent teams. Now, human-human teaming, what we want to do is, do humans adapt to each other in teamwork, and how we can characterize and quantify this. Because if we look at the human literature, the human team literature, what we see that people say, yes, adaptation is great, but they haven't really teased this thing apart. So the second part that we want to talk about is in agent-agent teams. Can we develop ways of having diverse agent policies? And are these policies in a particular domain really diverse? And human agent teams, can we quantify human teams member type and then adapt and see how now humans and agents could adapt to these different types? So our hypothesis, and we want to use a machine learning approach to develop the agent, but our hypothesis is basically this adaptation. Instead of doing this adaptation to each individual human, possibly we can see if we can have types of humans that then the agent policy types, so that then we can see if we can adapt, the agents can adapt these policy types to the type of human that they can understand, because they may not be able to understand with few examples of playing with the agent, with a human, the agent may not be able to understand exactly what this individual human is about, right? It would need many samples. And so the idea of types, that is also the idea of types in game theory, for example, different strategies, right? Game theory. So the idea here of having types and seeing if there are different types is to really be more sample efficient and actually see whether that is possible to have high performance team if additional adaptation is done. So the overall objectives, as I said, is that the agent would adapt to specific strengths and weaknesses of human teammates, that adapts a behavior that is trained to employ similar strategies for different humans. And what we want to do is to develop effective techniques to identify these player types and learn to improve player behavior. And also, eventually, what we want is to investigate not only adaptation, but also team stability, processes, and rapport with adaptive agents. So our test bed is a very simple test bed that we extended, is called Space Fortress, and we call it cooperative or teamwork, Team Space Fortress. Initially, this game was developed in 1983 for psychological experiments because it's simple, you can do controlled experiments. We adapted it, we extended it to have 2 players instead of just 1. Here, what we see is we have the fortress in the middle. The fortress is a shield, and the shield does not allow anybody to shoot it. However, if somebody enters its hexagon here, and the fortress will start shooting, and then another teammate can go, then the shield opens, as you will see, when you start shooting, the shield opens, and then the teammate, the shooter, can go at the back and shoot it. So the first player is called the bait, and the shooter is the second player that goes and shoots. So here we can say, okay, we can also, of course, have agent teams, and we can train some of these, and we trained actually. And here what we can see, they have optimal performance, but they are kind of totally surprising. They're unintelligible to humans. So if we just go blindly and say, let me develop agents that play optimally and then give that agent to a human, we may end up with a situation like this, where now the human doesn't know how to play with his agent. So the point is the following, that not only we want to use machine learning to develop agents, but also we want to develop agents that actually will be intelligible to human, and the humans will be able to adapt to them. That's one point here. So first we started saying, okay, since we are talking about adaptation, can we see if in human-only teams there is adaptation and what is the role of adaptation? So my psychology colleagues developed this very clever design where we had 4 people in squads. So we said, okay, we want to observe diversity in the player type, and then we wanted to see if composition contributes to team performance. And so this experimental design was as following. We had 2 sessions in round 1 and 2 sessions in round 2, and we had 26 graduate students in HRI at the University of Pittsburgh, and each student was randomly assigned to play the bait or the shooter role. And then they were playing together. And in each round, participants were divided into these 4-player groups, the squads, with 2 baits and 2 shooters. So after the first set of trials, so in the first set of trials, we have shooter 1, bait 1, shooter 2, bait 2. And then in the second session, we crossed them, right? We paired now shooter 1 with bait 2 and shooter 2 with bait 1. And after a month, we had around 2 of these experiments with 10 trials now, because they had learned, the people had learned, but we do the same experiment. And so the participants were, as we said, assigned randomly and then switched. So first of all, we looked for learning effects. And what we saw is we did observe learning effects in round 1. So this is the fortress skills, which is basically the performance characteristic, the performance measure. This death is basically the death of the shooter or the bait. And the shield opens is how many times the bait went in, the shield opened, but maybe the shooter was not successful in killing the fortress. Okay. And so we see different shield opens that are more than actually the fortress kills. Okay. And so what we see is the performance is stable in round 2. So there is no significant difference in average fortress kill in the first 5 trials and the last 5 trials. So we are, for the things that I'm going to talk about in the next slide, the performance, we use the round 2. And so what we see here in terms of the individual versus team contribution is very interesting, because in this squad 1 and this squad 4, these are examples, what we can see is primarily determined, the performance of the team was primarily determined by individual contribution. So here, this point here says that I have bait 1 paired with shooter 2. Okay, the color is the shooter and the x-axis is the bait. And here I have bait 2 paired with shooter 2. And the same thing for shooter 1, shooter 2. And what we see in these particular situations is that the actual performance of the shooter determined the skill, in other words, of the shooter determined the overall team performance, the improvement in the team performance. And here was the debate, actual performance. Oh, sorry. Whereas here, for example, what we see is that not only the individual contributions, but also team interactions were found to be significant. So, for example, in bait 5 and shooter 5, what we do is they have sort of similar performance here. But on the other hand, if I have, let's see, bait 6 and shooter 5 versus bait 6 and bait 6 and shooter 6 did much worse than bait 6 and shooter 5. So what we see here, basically, shooter 5 and bait 6, as I said, achieved better performance, though shooter 5 and bait 5 were better individual players. What is the idea here? The idea here is that we cannot really have 2 high-performing, skilled people and put them together in a team and expect that the performance of the team is going to be higher. because they may not be adaptive to each other. So the point then is that team performance is basically determined not only by the individuals, the skill of the individuals, but also the way that they can play well together. They can adapt together. Okay. And that we have seen, we've done some, by the way, we have done some experiments, some analysis with high performance baseball teams, and we found the same sort of thing. We can have stars and so on. The team doesn't perform well, whereas if you have a bunch of mediocre players and some of them that perform well together, then they get higher performance. So this is the take-home message here. And so the other thing we wanted to look is to see how exactly this adaptation happens. And what we found, and here's an example, is that basically the bait leads the shooter. So what happens is that not only there is adaptation, but there is also synchronization. So for high team performance, what we see is that there is a lag between the performance, and this is in this cross correlation here, because this shows the lag. And so what we see here is the highest cross correlation of the human, of the shooter and the bait working together is basically lagging the shooter. So the bait lags the shooter, and that gives the highest synchronization. This is what these things mean. And so team performance then, this is a take-home message. Team performance determined by both individual capabilities and team interaction. And we measured the similarity and distinctiveness among trajectories. So now what we want to do is to basically crowdsource trajectory comparisons and calculate similarity scores between trajectories to actually see, are there really similarities and differences between players. And so first of all, what we want to do, so we did an MTurk study where we asked participants to actually determine the similarity in trajectories that they could see. Because as you see, this is a continuous game, and it's a fast game. So it is not very obvious what these trajectories, what the similarity of these trajectories would be. So, oops, all this, I don't want that. What do I do now? I need to get back. Sorry, I need to get back and get myself here and get it here again, and hopefully it will be fine. So what we did is we have MTurkers, we gave them 3 short videos from trajectories of display, and we asked them to determine which of video B and video C, whether they saw that it was video B was more similar to video A or video C was more similar to video A. So we wanted to see if humans would actually make a determination of similarity in trajectories. And what we found is that yes, indeed they could. And we, here I won't go into details, but what we want to do is to have here, we have an example of one squad. Shooter 1, bait 1 is the red dot. Shooter 1, bait 2 is the green dot, and so on. And what we found is that shooter 1 exhibits higher adaptation when paired with different baits based on the distance average. So this one here, the red and the green, whereas this one's was not good adaptation. And the thing that we found what was interesting is that in this particular case, the performance of the team was bigger. So we also were able to find that, again, that adaptation means higher performance. And here I show the actual numbers of what we show in the previous slide. So basically what we said is to decide that shooter 1 had a bigger index. So you see here that there was a significant difference between shooter 1 and shooter 2. And this is the p-value. whereas shooter 3 and shooter 4 did not have, and so on. So shooter 1, shooter 5, and shooter 8 had the biggest adaptive index. Now, we said, okay, this is what we decided and what we found in human-only teams. And what we found there is the composition and the skill play role. Now here, what we want to do, of course, since we are talking about human agent teams, we want to develop our agent library, our agent policies, the different types of agents. And what we did, we developed this using training approaches as heuristic policies, reinforcement learning policies with reward shaping and imitation learning policies. And in this way, we developed a library of 7 shooter policies and 9 bait policies. And we, using self-play between agent-agent teams, now we were able to develop a performance of these agent-agent teams. So here, for example, is video of this mirror policy. And what we see, for example, is that as the bait goes in, you see they're symmetric, right? They are trying to align themselves. So this is basically one of the strategies that we found was very interesting. These are the reinforcement learning agents. So we train them to avoid walls, to stay in front of fortress, to avoid collisions. So this is the way of the reward function that we used. And for example, here I show aggressive bait and defensive bait trained by reinforcement learning. So we see when it gets in, immediately the shooter gets in. Here it's more defensive. So the bait gets in, and the bait gets in and out because it tries to protect itself, but keeping the shield open for a longer period of time, so the shooter has a chance to come and kill the fortress. And so what I'm showing here is that basically by giving different parameters to our policies, we can make aggressive baits or defensive baits. We can make different types of baits, for example, in shooters. And here we show a little bit the imitation learning agents. And so since the agent needs to exhibit human-like behavior while also performing the task, we created loss functions where we had trade-off between imitation learning and reinforcement learning. We created policies that would have these good trade-offs. Why? Because as we showed at the beginning, if I train only agents for optimality, that means I train them only for the reward function, then they may be unintelligible to humans. They may not be able then to cooperate with the humans. Whereas if I have imitation learning, then imitation learning does not go for optimality, but goes for similarity to human trajectories. But on the other hand, it does not perform very well. So the point is to create a kind of good compromise between imitation learning and reinforcement learning. And so this is what we're talking about here, collected different agent training algorithm that blends imitation learning and reinforcement learning. So the other thing that we wanted to see is, do we really have types? Do we really have differences within each of these roles? And so we did a PCA, and here is an example where we really see that a particular bait 6, is really different than bait 8, right? Because in the PCA, when we take their multidimensional performance and we project it on the 2D environment with PCA, then we really get these distinct clusters. So here is this agent-agent performance library that we got by self-play between the agents, between themselves, all the agents that we have. And so what we see is that really we get different performance. For example, here we get with bait 3 and shooter mirror 1, we get really high performance, whereas if we have shooting mirror one with all the other baits, we get less good performance. The same thing, for example, for bait. For bait here, we see that for bait 7, we can pair this bait 7 with different shooters, but basically shooter mirror 4 gives it the biggest performance. So here we can see basically which are the what we call the complementary pairs, the complementary policies. Complementary policies means the policies that will give you the highest performance. And then the idea here is that to see how are the human players policies compared to agent policies? Can we actually determine whether how to make similarity judgments between human policies and agent policies? Because the idea of doing this agent library and the different types of agents is the following, is to look at human trajectories, determine in a particular role, determine which are the agents in the agent library that gives the highest performance, and then the agent then adopts the complementary policy. So let me go to make this because it's a little bit convoluted. So suppose that I have a human that is a shooter and I have a bait that is the agent. Now suppose that I get the human's trajectory and I determine, the human is the shooter, remember? I determine that this human's trajectory is the most similar out of all the shooters here with shooter mirror 1. Then I say, and my bait, suppose my bait initially was playing bait C2. Okay. Now my human is playing shooter against bait C2. However, when I see the policies of the human, I go in my library and say, which is the closest agent shooter that this human trajectory is similar to? And suppose I get shooter mirror 1. Then the agent, it's not I, it's the agent now says, okay, since the human behaves like shooter mirror 1, I should switch from seed bait 2 that I was playing before to bait 3, right? This is the whole idea. And so this is what we want to do. And so what we did is we collected 54 human participants. And what we did is we basically had them playing with all the agents in the library, in the roles. So each human participant took the bait role, he played with all the shooters, and also then he took the shooter role and played with all the baits. So here, first of all, what we can see is that using a cross entropy measure, we use that measure to calculate the distance, the difference between the similarity, in other words, between the human policies, which we don't know, right? We cannot control the human, with the agent policies. And of course, the human policy is expected to be non-stationary, so SEM is calculated over time using sliding windows, because as we saw before in the human-human experiments, humans learn. Not only learn, but they adapt. And so possibly, if the humans adapt and the agents adapt, we may have a big non-stationary evolution of the team, which is difficult to calculate. So here, first of all, what we want to see is, does this measure, this cross-entropy measure, really give us some reasonable results? And here is an example. And we say, okay, here we have our bait seed here. And here we have this other bait, right, that we showed before. These are two different types of baits. And now when I plot the human policy, then what I see here is that all these green dots that indicate the human policy are in the cluster of bait seed 8, which tells me that the human policy is very similar to bait seed 8. We can see that from the cluster, and this cluster is what the similarity metric also gives us. So that's all well and good here. And so now we want to say, how do players' policies not only compare in terms of similarity, but actually can we see which they are closer to in all the agents that we have? And so what we see here, we have the human policies that are all these dots that are in the shades of blue, so to speak. The squill agents, which are the soft Q imitation learning, that is a variant of what we did with respect to taking a compromise between imitation learning and reinforcement learning. So this is our variant of squill here. These are the red dots. And then I have the RL agents, the pure RL agents, which are with triangles. And so what we see is basically that the squill agents in the human policies are closer. That's good. It's a sanity check, right? Because you train these agents and you have no idea what you're going to get, basically, right? So it is a sanity check. And here we can see for the human baits and also for the human shooters, the same thing that the squill agents, we can see that, okay? And so what we want to do is, as we said, we had the trials with each agent. The human shooter bait was paired, and our distance measure is the cross entropy measure, as was said before. And then what we wanted to look at is now if I go and look at the complementary policy that I get from the library, is that going to really increase the performance? And so what we see here is we have, so we called it similarity to optimal. And this is the distance between the human policy and the complementary match for the agent that the human was playing with. In other words, initially I determined which was the one, the human with an agent role, and I picked the complementary agent policy. And what we see is that this similarity to optimal, basically, if it's more similar, if the policy that the agent adopts is the complementary one to the human policy from the library, this is positively correlated with team performance in both bait and shooter, and it explains 70% of the variance in performance. That's very important. That really this similarity is explaining the 70%. And so here we can see that over time, here's the regression lines here, that we can see that indeed the performance increases as the similarity increases. So this is similarity versus performance, right? And we see that both of them increase, both for the shooter and for the bait. So we're in good solid ground with respect to this. And now we say, okay, now let's see if this adaptivity in the agent. So now we go and have particular adaptive regimes of human and agent teams. And this is what basically I've been saying all along in terms of actually getting the similarity with a human in an agent library, and then the agent gets the complementary policy. And so here again is the similarity metric, is the cross entropy and self-play performance from the policy library that we have already seen. And then basically what we do, the adaptation procedure, is to infer the most similar agent policy and select the complementary policy. This is what we've been saying all along. Here we are just recapitulating. And so what we did three conditions in a new experimental design, where we have 134 participants from men to Turk in 3 between subject experiments, and with 3 regimes of agent policies. The one is the adaptive one. So it identifies the policy most similar to the human in previous trial and adapts the complementary policy. So what a human does, it sees what it plays a trial with a human. So the agent plays the trial with a human. And then what it does, it says, okay, let me see now what is the similarity of this human trajectory, this human play from the library. And now I adopt the complementary policy. And every trial, it may change, the human may change his policy at every trial. So the agent, after every trial, also changes its policy. So it is really very adaptive, trying to actually capture the learning and the non-stationarity, so to speak, of the human policy. Because the human could say, well, I played policy. I mean, we don't know. We don't really know what the human policies are as such. But the human may say, well, you know, I think I played well, but let me try something different now. And then he changes his policy. So now the poor agent is trying to now catch up, so to speak, right, with a human. Okay, so this is the adaptive one. The fixed one is it selects a single agent policy and maintains it throughout. So it doesn't change, it doesn't adapt at all, it is fixed. And so here we want to see what is the effect of the human adaptation, because the policy of the agent is the same in all the trials. And then the third one is the random, which selects a random agent policy for each trial. And so we want to see the effects of the human adaptation for each trial, right? Because each trial, the agent changes. So now we want to see how does the human now change to a changing agent, or does the human keep a fixed, consistent policy? And how is the performance then of these done? And so here what we see, which is kind of interesting, so here are the learning curves. And so the adaptive agent has, in general, it doesn't start being with better performance, but as things progress, what we see, it gets a bit of higher performance for if the agent is a shooter and the human is the bait. Okay? It's not, the difference here is not significant. Here, however, the difference is significant when we have bait agents and shooter humans. And what we also see is that for bait agents, there is significant difference in team performance. So the adaptive agents outperform random, but not fixed. It's kind of the P is close to 1, it's not 0, 0, whatever. But on the other hand, the adaptive agent achieves team performance faster than the fixed policies. So although they do not outperform the fixed policy, they do converge faster. And in particular, in trials 6 to 8, the adaptive group significantly outperforms. So here we see the crossover. As we see all of a sudden, you know, in 6 to 8 trials, we don't know why this is happening, but the adaptive agents really seem to outperform both the fixed and the random. And so here's my summary. So first of all, in human-human teams, what we have found is that team performance depends on a combination of individual capabilities and team adaptation or team composition. High performance teams exhibit synchronization, basically, where the shooter behavior lags. So it's not only adaptation, but in this kind of game, for example, one needs also to be synchronized with a teammate. And adaptive shooters have higher team performance. In the agent-agent teams, what we did is we had, first of all, to construct a library of agents that would cover a space of what we thought may be human performance. Because first of all, you need to have diversity if you have training, and also humans are very diverse. So this is, the whole enterprise is much more challenging than this multi-agent RL and so on that we see in the literature. Why? Because the humans, we cannot control the human policy. I mean, it's one thing to say, okay, I'm going to have a centralized regime system for multi-agent systems and then tell each of the agents how to behave for the optimal performance of the team. And this is what most of the literature, or all of the literature basically does in MARL, MA-RL, multi-agent RL. But the moment I have the human, I have no idea what the human's policy is. And as we saw in our experiments, humans also may change their policy significantly from trial to trial. And so that's the whole issue here. And so we are looking then at constructing agents with diverse policies, so as to be able to cover the space to anticipate what possible human policies may be. And agent-agent performance can be empirically determined with self-play. And again, with agent-agent performance, we found the same thing, that it depends on team composition. So these two things, we established the fact that really performance depends both on the skill and the adaptation and the composition. And now, based on those results that we have, we go to human agent teams. And because we don't know the human policy, we need to find a measure to determine the similarity of the human policy with the agent policies. And we found this cross-entropy measure. And then the human similarity to the most complementary policy is predictive of team performance. This is the slide with the 70% of the variance accounts for the 70% of the variance. And now then, if we get the agent then to adapt and adopt itself the complementary policy, then this allows the team to achieve high performance faster. And of course, this is the preliminary results that we did, and we showed that actually an adaptive policy is better than the random, but may not be better than the fixed in all situations. And so, of course, we did only 50 people and so on. So one could do more and understand. Another thing that we are doing is we are currently collaborating with neuroscientists for measurement of brain activity via fMRI during human agent team play. So what we have is we have an fMRI, and the human is playing within the fMRI, that within the whatever we call this apparatus, that you put the person in it and measures the brain activity. And that person is playing with our agent in a bait or a shooter role. And so what we want to see is really what are any brain correlates, neuroscience correlates of the brain team activity as the person is playing. And as the person is changing its policy, for example, or as the person sees the agent change its policy. So these are experiments that are currently underway, performed with colleagues in the neuroscience department. That I think would be very interesting to see. And the future work, so here in the studies that I talked about, we had a dyad, basically, a human and an agent, or two agents or two humans. And here what we want to do is basically to extend that to the loyal wingman scenario, so-called, where we have a human piloted aircraft and we have various UAV agent wingmen, right? So now we're going to have a team of three, where now it's very heterogeneous, because here's the human and the two. These two will need to cooperate among themselves, possibly, and also cooperate with the human. And another thing that we are introducing here is the limited field of view for each one of them, so that we can examine things about trust, about limited information, about what communication. So what kinds of communication is going to be effective for among these three entities, these three teammates, for high level team performance, and also what kind of trust. So for example, if I have this wingman telling you, oh, there is a high value target here, and if I have the other one telling you, no, there isn't, then what is the human going to do? And these are very realistic kinds of scenarios where we have these kinds of confidence of conflicting information, basically. So what is the human going to do there? If it believes the one, or does it ask him to get to get additional evidence and so on? So these are some of the things that we're looking at. And these are some of the research themes that I've kind of talked about. Basically, the learning of human agent communication, what information should be communicated, when should be communicated, and with what fidelity. If you have done work, if you look at the work in multi-agent reinforcement learning systems, the neural networks emit a communication each time tick. But if you have an agent that each time tick now tells the human something, the human is going to turn it off. So the point is that we need to have our trained agents understand when to stop, to not communicate, and when to communicate. And that is, again, an area that has not been looked at all. Okay. And then in terms of the trust calibration, high levels, low levels, what does the human do when it has high level or low level in the wingman of trust? And also, what can the agents do if they actually feel that the human doesn't trust them? Okay, we had done some of that work in for human and swarm that the brother talked about, human swarm interaction and trust between humans and swarms. And the idea is that if the swarm thinks that the human doesn't trust it, then what it tries to do is become more predictable. Say, okay, more transparent, okay? So that to show the human what is happening. And so here we are going to also look at these kinds of research questions in this teamwork of 3, where now we can have pair-to-pair communications or broadcast multicast communications. And here is my team, and I thank them for their contributions. And thank you all for listening. Thank you.
Thank you so much. I'm going to applaud on behalf of everyone. This was a very, very interesting presentation, and very intrigued by a lot of the things that you mentioned. There's a few questions here. I'm going to read out the first question that came in. This is from Tim Klausner, and Tim asked, how well do you think the cross entropy measure captures aspects of policy similarities and differences? Have you seen policies for which cross entropy is not a good metric?
Yeah, so we used, I think we captured it. We think that we captured the similarities and differences pretty well. And actually, this cross entropy measure is important because it actually, with some adaptation, and they have the reference. So the idea is that here you can actually sample from a policies that you don't know, and because we don't know we know the policy of the agent, but we don't know the policy of the human. And so with few, so the idea there was also with few samples of the policy of the human now to be able to do this determination. Because obviously, if you take trajectories, right, and you say what are they, then you have an uncommon. I mean, if you look at in terms of points, you have trajectory, you have an uncountable number of points you cannot sample. So the idea is, how do you take few samples? So we thought that this measure was very useful.
Awesome. Ben Schneiderman has a question. Ben, if you want, I can read it out, or if you want to unmute and ask it directly, you can go ahead.
Thank you. I'm intrigued by your talk and the psychological foundations of what teammates might be like, but I'm troubled by the notion that you seem to believe that human-human teamwork provides a reasonable model for the design of computers. I see little evidence that the social assumption that computers as social actors, Cliff Nass and other work has proven to be valuable when computers have such distinct capabilities of storage, speed, large displays. Do you have any examples of existing systems that really make use of the teammate metaphor? It just seems.
Well, the point is that that humans have to work with what we call agents, and whether we want to call them intelligent agents or learning agents or computer programs or whatever, we can call them whatever. But the truth of the matter is that there are going, and this is of course very simple things because we wanted to examine a particular aspect of the adaptation aspect. But the thing is that humans and agents are going to be working together.
I don't agree. I don't agree they work together. Humans operate machines. I mean, I don't know any existing technology where there's a sense of working together. I mean, a camera or a car. I drive a car. Even, when you use an autopilot on the plane, the name, the pilots are still sense of they are flying the planes. They're responsible for everything that happens. They invoke the autopilot, and they turn it off and they monitor its behavior. But I just don't see that the widely held belief. Your position is widely held. Mine is the minority one. I'm looking for the examples that give me more belief that it's going to work.
Well, so this is of course is research, and so it's forward-looking, and so you can imagine in the future that you are going to have squads of robots working with humans, clearing rooms in an urban search and rescue scenario, or finding victims in a disaster relief scenario. And then the point is that they are going to be communicating somehow with the humans. And
the model of human communication does not prevail. In disaster robotics, Robin Murphy and many other works have shown that the voice interaction with disaster or search and rescue robots just doesn't pay out. And a visual display conveys so much more information that the human model is misguided.
But of course, when I said communicate, I didn't say in text or voice or whatever. It could be visual displays, and the robot also could be shown visual displays and recognize things. As a matter of fact, we have another project where in simulation, of course, but to look at some results where the idea is that I have a disaster situation and I have you can think of Fukushima or whatever, something is happening that is really very dangerous to human. And so I can send a robot into a building that is collapsing or is dangerous. And then the humans are outside. And now they are trying to actually communicate via language, as a matter of fact. I mean, we don't take the noise and all these things, this is a simulation. But we have the robot, the agent, inside the building, and the agent goes around, recognizes things, and so the human can say, go find the victim, or go find all the victims. And of course, the robot has been trained to be able to recognize when it sees a victim. And then when it recognizes in language, translates that into language, with visual recognition into language, that then it says, I have found the victim. What do you want me to do next, for example?
But neither disaster robots, nor drone operations, nor Mars teleoperated rovers follow that scenario. I'm still looking for an example that.
Well, if you have Fukushima, you may want to have that scenario. Because then your robot is inside.
It was a teleoperated robot. It was not.
It was, but we are talking about not going away from teleoperation and having autonomous robots. This is future. This is not.
I think there's a better future possible. Thank you.
Maybe. Okay, any other questions?
Uh, yeah, I had a question about the recursive aspects of this. So there is recursive modeling happening here, right? As in the humans are modeling what the agents are going to do, and the agents modeling what the humans are going to do. And so there is you could take this one level further, and the agents could model what the humans could be modeling them, and you end up with this recursive modeling thing that people have looked at in the AI literature for a while. So I'm curious if there are aspects of that you have incorporated over here, or how would recursive modeling change the performance in this case?
Well, actually, this we are going to go in a very non-stationary situation, right? And the recursive modeling, we have avoided it for obvious reasons because of the computation capability, basically. And so, I mean, this is one answer. And the other answer is we want to see, is it possible to get any reasonable results, for example, with not going into the second level of modeling, right? Because recursive is, you go into these different lies. And that is very interesting what you are saying, but at the beginning we're just cutting it into, the first one. But we are indeed faced with this situation of recursive modeling in another project, which is basically an agent that tries to look at behavior of human performance, human team performance, okay, all humans, and now is trying to understand, and of course the humans do not see one another. They're again in a search and rescue situation where there are different parts of the building and so on, but they're allowed to communicate with each other, with their teammates. And so now the agent has to look both in terms of what each one of the teammates is doing, and also look at their communications, and then be able to understand deficiencies in the teamwork and help. So for example, if suppose we are three, player one, player two, player three, all humans, suppose player one sees a victim, for example, right? Mm-hmm. And the player one is not a medical person. So it says, okay, communicates that to the medical person, but forgets if it sees, for example, that there is a rubble in front of a room. So suppose there are three roles, right? The one is the scout, the other is the rubble person, and the third is the medic. So now if I'm the scout, I go and see a rubble. Okay, I communicate it, let us say, to the rubble person, because that's obvious to me that, okay, the rubble person needs to know. But I forget to communicate it to the medic person, although it could be relevant to the medic person. So now the agent could actually see and say, oh, this is deficient because the medic person knows. Now the point is that the agent, however, needs to make also the second inference, mm-hmm. and say, now, does the medic know that the rubble player knows? You see, and then you can go into the rabbit hole, and it knows that it knows, and who knows about what the other one knows, and so on. Right. Mm-hmm. So that modeling that is really, and very interesting.
Right.
In a distributed way.
Right. So on a related note, I'm curious if in this specific game that you use as case study, there's no explicit communication between the two agents or the human and the agent, but I'm wondering if there are ways to express intentionality by through your actions, right? Because I'm assuming that the other agent or the human gets to observe what the other your teammate is doing. Yes, for lack of a better word. So could you, for example, have policies where you force your partner to take up a specific role by expressing sort of through your actions that this is specifically the role that I am going to take over here?
Yeah. So you really nailed it. Indeed, this is true, because in the team space fortress, the agent that enters first, by definition, becomes a bait. by default, because the fortress immediately, each time the fortress is anything in this hexagon, right, it starts shooting at it.
Okay.
So if I am, so it's exactly this. So if I am the agent, and I think so, as a matter of fact, what we have as another future work that we want to do is actually to see the agent making critiques of the human's performance. So, saying, look, this person as a shooter is probably better. I mean, he's terrible as a bait. And so maybe I will force him to be the shooter by entering first.
Right. Okay. That makes sense. I'd missed that specific part.
Yeah.
We are a couple of minutes over, but so last call for questions. Any last minute questions for our speaker? I have a couple more, but we can do it offline. Okay. Looks like there's no more questions. So let me thank you once more for a great presentation. I think this was very, very informative. And I think I'm quite excited by the future research directions over here. So look forward to seeing results on that front. Thank you again to all the audience. And we have a few more seminars left in the semester. So make sure that you go to the Robotics UMD website and sign up for the upcoming seminars. So with that, I'm going to stop the recording, but thank you. And hopefully all of you have a good weekend.
Thank you very much.